Good evening and welcome to the week 12 of the live interactive session of the Fabrication Techniques for MEMS-based Sensors, a Clinical Perspective. The course instructor is Professor Hardik Jitendra Pandey of ISC Bangalore, and I am the teaching assistant Vikas Pandey from IIT Jodhpur. Just a brief about me. The YouTube channel where every video is uploaded, and the email you can contact me. And this is the 12th week, that is the last week questions. Along with this, day after tomorrow, we will be taking an additional uh, class on which we will be discussing the whole microfabrication flow. You can join that also. And before moving to questions, if you have any specific doubt, you can ask. We can then continue to the questions. Any doubts? And that CVD and isotropy, that I will cover. Like CVD I will cover today, isotropy in the next class. Like while
Oh,
discussing the etching profile and all, I'll put that.
okay, sir. Thank you.
Yeah. Any other doubts or questions? Okay. So let's dive into questions now. A microfluidic device with two inlets and four outlets had a channel dimension of, so it is having two inlet, okay, and then on the chip, like we have the microfluidic channel, and at the last we have four outlets, okay, and it is saying that such that 5 microliter per minute blood and buffer solution need to be injected at the same time into the chip. This fluid flow through microchannel can be achieved using which of these? Centrifugal pump, peristaltic pump, inline sump pump, or rotary lobe? Yes, any answers?
B, peristaltic.
Peristaltic. And why B? Is there anything special in peristaltic pump that makes it possible to have such a configuration?
It's a micro channels through which we can send such a low flow rate,
Hmm.
the fluid with such a low flow rate, like in the microliters per minute.
Yes, so
And
we can flow like very small flow, we can achieve very small flow rates using peristaltic pump, right? So this is the correct answer. Only predefined multiphysics can be used in COMSOL multiphysics. So are you aware of COMSOL? Yeah.
sir, I have to go through these two models, last two models.
Okay.
Just I'm aware that this is a simulation software,
Hmm.
but not much more about it.
Okay. So is it that only predefined multiphysics can be used in COMSOL, or is it that we
I
can
think it is false. It is not.
yes,
It is false.
yes, because we can create our own modules and libraries, as well as we can create
Yeah.
our own multiphysics and add them. What is the flow modeling order for FEM simulations in COMSOL? To make geometry for the like, this is the steps we have to arrange them in correct sequence. So any idea how we can do this?
I'll
Yes,
just try because as simulation is to be carried out, so first we have to make the uh,
mhm.
geometry, then go for choose the type of study. After that,
Geometry,
select
then choose the type of study. Okay,
type
after
of
that,
study.
Hmm.
Then to add materials, then apply physics conditions and post process. That is
Okay,
what
so after
the
this,
gates. I'm not so sure about.
yeah, yes. Arvindji, would you like to add something to this?
No, sir, that was I thought
Hello,
the same.
your voice is very low. Like I'm not able to hear you clearly.
Sir, I thought the same, sir.
Okay, right. So, post processing is the last. So we should start from A, that is make geometry, right? Uh, choose type of study, and then yeah, go to add material. So it is first we make the geometry, then we add the material, apply physics conditions. It was there, right? Choose type of study. Okay. First we are adding materials, right? Uh, so geometry and materials. Then apply the physics conditions, type study, and then post process. Fine.
Okay.
Yeah. It is like when we are choosing the geometry, we don't directly go to choose type of study. We first move towards like it will we add materials, and then we move towards applying physics conditions, and then we choose the study, and then the post processing. Slight variations, right? Okay. A biochip for gas sensing was designed with ID for detection of biomarkers in breath. When compared to traditional ID, requires high volume sample and has improved sensitivity. Thus, does this argument hold true irrespective of sample? It is saying that a biochip was designed that for detection of any biomarker like acetone, like whatever is the acetone, ammonia, or something like that. When compared to traditional ID electrodes, it requires high volume sample and has improved sensitivity. Is it true for any sample? That for any kind of sample, when we are uh, making a biochip, it will give uh, improved sensitivity but require high volume samples.
I thought it's false, sir.
False. And what should be the correct answer? This is not fixed, right?
The
It will,
amount of volume is not important.
yeah. And
Lower volumes is also sufficient for
so,
testing.
yes, because we can go for smaller volume also. And in fact, the advantage of a biochip is generally that we are using small volumes.
Yes, sir.
Okay. To model a MEMS microheater. So we have been learning about microheaters from our first week itself, like a microheater, a microheater. We want to model it in simulation. Which physics will you solve for? Electrical and structural and physics, structural and thermal physics, electrical and thermal physics, or fluid flow and mechanical physics? Yes. Any answers on this?
Electrical and thermal.
Electrical and thermal. And why thermal
Maybe.
is important? Because we are actually dealing with heat. What heat it will generate, right? And in any other, yes, you were saying something. Continue, please.
No, sir. No. Not.
No. So it is electrical and thermal physics because like electrical modeling is required so that we can understand how much current will flow through it, and at the same time how much heat will be generated, or what will be the heat profile, right? Suppose we want that on this microfluidic chip in this area, what temperature should be there, right? So at to achieve that temperature, what will be the flow of the current through this? So what will be the
See,
applied voltage?
not clear.
Yeah, my voice is not clear.
Yeah, yeah. It
Okay.
seems can ask the other participants also, but
Yeah,
yeah,
Arvindji, are you able to hear me properly? Or
Yes, yes, it's audible, sir.
okay, so Nilmaji, you can just try to disconnect and
yeah,
connect
just
again.
rejoin. Yeah, yeah,
Yeah,
sure.
please.
Sir, is
Yeah,
that the CAMSOL is a open source software or is it a paid version?
I think it is not open source. Uh, COMSOL multiphysics, I'm not sure whether it is open source or not. I think it is not open source. Uh, I'll have to confirm. I'm not very sure. Yeah, now you can hear me, Nilmaji.
Yes, yes.
No, fine. So it is the electrical and thermal physics. Why electrical? Because we want that to know at what electrical condition, what thermal conditions will exist, like at what voltage and what current we will get the required temperature or in on the area, our active area. Okay, so these are the two things that we require. Bonding PDMS to glass can be achieved using oxygen plasma chamber, adhesive, UV chamber, or RF chamber. Here, most of the things are repetitions, right?
Yes. It's
So,
oxygen plasma chamber.
yes, so it is oxygen plasma chamber in which bonding of PDMS and glass can be achieved, right? How can a perfect bubble-free PDMS be obtained to fabricate a microfluidic system? So, to create a microfluidic system, we are using PDMS stamp, right? Or also known as uh, what is the term used for that? Using the PDMS stamp? Yes, anyone?
Is it a flexible sensor? That
Hmm. Like the process, I am not talking about the
okay.
result process. Mhm. Soft lithography,
Soft
I think.
lithography.
Yeah,
Yeah, soft lithography.
we discussed this also. So using soft lithography, we want to that, but actually, some bubbles can be formed. Okay, so how can we make a perfect bubble-free microfluidic system? By using periodic degassing, or using hot plate, oven, or cryo treatment.
In the video, it was shown desiccator is used
Yes.
to extract the air bubbles.
Mhm.
But here, the desiccator is not given in the
Yeah.
options.
So you are in the right direction. I think seeing the options, you will be able to find out which option is correct. What is being done in the desiccator?
So making a vacuum, creating a vacuum inside.
Yeah. So we are removing gases from there, right? So that
Yes, yes,
process is called as degassing. Okay. So it is done by periodic
desiccation.
degassing. Yeah. And hot plate we cannot go since that will make it very like that will not make result in even surface. Oven and hot plate are same thing, and cryo treatment is also again like where we will be freezing the things. There also uniformity will not remain, like that will shrink and thus. So it is by periodic degassing. Fine. So
Yes.
this is done using putting in desiccate. Okay. Okay. So one more thing that has been talked in this week is 3D printing, and this is something that is very commonly being used nowadays. in many industries, and in fact, it is considered as something very revolutionary in the field of manufacturing and as well as this construction. Okay, so what is the file format used for 3D printing? Is it GBR, STL, XLS, GDS? Yes,
It is STL, sir.
STL
Second,
and
B option.
B option. So, and what does this STL stand for? Any idea?
Yes, I was aware, but not able to recollect it. Just give me a
Yeah,
second. Note
it
it
is.
down somewhere. That is STL is that stereolithography only, that right?
No, it is standard triangular language.
Oh, sorry.
Okay,
Standard.
triangular language, and the name is very peculiar. Okay, this is actually 3D printing is a quite old technology. Like it is not very new, but it has been adopted very recently, and it has developed very like it has grown very recently. Like for 20 years, it was under patent, and in fact, the company that made it, or the person who made it, and he made a company. It didn't grow that much till it was under patent, and he developed this STL thing. So it is like uh, the whole structure is since we have 3D structure. So like if we have something like this, some structure like this in 3D, so it is something like we have to print it layer by layer. Like we have to put one layer, then above it another layer, like that. So it is cut like digitally. The whole layer is cut. Whole thing is cut in layers, and then on the planar thing, like if you see it from the top, like if the structure is like this. Suppose for this layer it is like this. For the next layer it is something like this. Then another layer. So again, this was divided into triangles, like crisscross thing, and here triangles were formed. So this file format is known as STL, Standard Triangular Language, and still that is the standard being used throughout 3D printing. Fine?
Sir,
Yes, yes.
standard tessellation language. I hear somewhere.
Yeah, standard.
Tessellation language.
I didn't get
TESSELLATION.
S S C.
Tessellation. TESSELLATION.
Okay.
I don't know actually the meaning of the tessellation, but I hear some standard tessellation language used for 3D.
Yeah, actually there are other uh, file formats like OBJ also, but STL is the most common one because this is like when we are going for the 3D printers, and some people, some proprietary items, what they are doing is that they are creating some other extensions for it, but mostly it is some variation of STL only. Okay, so there are other file formats like OBJ, and but they will carry some more information which is not relevant to 3D printing. Like because 3D printing, the material is not decided by the software; it is divided by the person printing it. So OBJ will actually contain material information, material reflectivity, and these things which are not relevant to 3D printing. So what it is done is that again from this only that relevant part of which is relevant to be given to the this. 3D printer, that is taken out. And anyway, STL cannot directly be printed. It will have to be converted into machine code called as G code. Okay, and then it is fed into the 3D printer to print. So, like from your CAD software, you generate the STL or OBG. OBG also works, and then you convert it into G code, and then you put in the 3D printer. So this is the standard file format for this 3D object. And nowadays you must have seen, if you are a Windows user, in Windows there is a 3D viewer, and now you can directly see their STL files. Earlier this facility was not there, and now you can easily see 3D objects, and even in PowerPoint and all, 3D objects can .stl files can now be imported. Now, again, this is something I think we are repeating it many times. Optimal incubator
Sir,
settings for a, yes.
just I would like to interrupt you on this because in the book which are the book on the sorry the lecture na they have
Mhm,
mentioned that STL stands for soft lithography, which is the file format you are telling na.
mhm.
So
So
I'm like
it,
bit
it is no, that STL soft lithography is a different thing. We are talking in terms of 3D printing.
yes, sir. For 3D printing only, when they were discussing the or explaining
Okay.
that code transfer, na, that CAD
Mhm,
software. So we have to
mhm.
prepare it with the CAD, and then CAD files will be converted to STL and then further to G code. That
Okay.
time, just specified STL. The long form is soft lithography.
Okay.
So I'm a little bit confused now. So I
Yeah.
thought I'll ask you
No,
again.
what I have like
Huh.
STL I know is
Okay.
standard triangular language, and that
Okay. Okay.
because I have
And I
spent
may
it.
have
Yeah.
some
Yeah. Yeah.
understanding that I may
Yeah.
have heard something. I
Yeah. Or
just recall.
maybe
I
like
thought I
I will also cross verify, though I have
yeah.
been with this term from last 5 6 years, I think more than that maybe, and I have always always found it to be standard
Oh,
triangle language or standard
okay.
triangular language only. So I will just
Okay.
check,
I thought I'll
and
just clarify
yeah,
myself. I may have some
yeah, yeah,
misinterpretation. I'll just verify. I'll
yeah.
also verify.
As much as I know, it is standard triangular language. Okay, I will also cross verify. Maybe something might be in my brain, and I am putting maybe confusing. But what I know is standard triangular language.
Okay,
Okay,
sir. Okay.
I will cross verify. Okay. So, what is the optimum incubator settings for a cell culture? This is a repeated question, so I think,
Yes.
yeah.
A.
A, 5% CO2, 37 degrees Celsius, and 95% relative humidity. So, cross-linking agent is not used along with PDMS elastomer to improve its mechanical strength. So, is it true or false? With PDMS, it is saying that cross-linking agent is not used to improve its mechanical strength. So if we are not using it, it will improve the mechanical strength of the PDMS elastomer. Is it true or false?
Is it a curing agent is the same cross-linking agent or it is different?
Yes.
It is same. Then in that case, we it the sentence is false then.
Yes. So it is false because it is used to increase. Anyway, seeing the wording itself, you can understand if something is getting cross-linked properly. Like if there is a structure and there it is getting inside it, everything is getting cross-linked chemically, or cross-linking bond is there, it will anyway improve the mechanical strength. If we see in terms of buildings or any material, if there is cross-linking in between, certainly that will improve the mechanical strength. And it is saying the opposite. It is saying that cross-linking agent is not used to improve the mechanical strength. So certainly it is right. A biochip for gas sensing was designed with interdigitated electrodes. So when compared, okay, it is this question is repeated, right? This was question one also. Is this the same?
Yes, yes, it is the same.
Okay, sorry. So I have put the same question twice. Okay.
No,
Okay.
I guess it is some different, sir. Does
No,
this argue? Yeah, yeah, it is same, same.
it's the same. Yeah. Okay. Which material is usually used for 3D printing application? PDMS, PEDOT-PSS, polylactic acid, or Teflon? Yes, any answers?
Polylactic acid. C.
Polylactic acid. Okay. Any other material you know which is used for 3D printing? Yes. Anyone?
No, sir, not at mine. This only I read it in the. All right.
Yeah, Arvindji, would you like to add?
No, sir, I thought this one.
Uh,
Polylaminoids.
yeah, this is the most common one, and it is generally used because it is easy to make, non-toxic, biodegradable, since it is made from, like you can say, it is mostly plant stems, this sugarcane stem and all that is used to make it. So it is biodegradable, and then it can come in multiple colors. Okay, but apart from this, there are other materials also, like the normal plastic we use, like keyboard, mouse, and these things. So what are they made of? Any idea on that?
Is it PV
Mhm. PVA.
no,
Any other material?
acrylic? Acrylic is the one.
No, I am talking about mouse, like this casing of our phone. Not phone. Phone actually use a lot of materials, like normal plastic materials, like headphones and these things. How are they made of? What are they made of? Not how. Sorry. Any idea? There is a material called ABS. Have you heard of it? Hello, am I audible?
Yes, sir, you are audible. I've
Yeah,
not heard about.
yeah. ABS, like mostly mouse, keyboard, and these things, and most of the plastic objects hard plastic objects we see, those are made up of ABS. And 3D printers can also print ABS, but the problem is that while printing ABS, it like it emits fumes that are like dangerous for us to breathe. So, and generally 3D printers are designed to be used very commonly. So if you have a closed kind of 3D printer, which it can close and there is a proper exhaust, you can print ABS, PETG, a lot of things. Like three common materials that are generally used are PLA. PLA is the most common one, and you see like different colors. That is the advantage of it. Different colors, but a bit lower, like when you print it, it will be a bit lower in quality. It prints around 180 to 200 degrees Celsius. It can melt and then it is printed. Then the second one is ABS, the best print you can get, but the problem is that it is a bit toxic, and so like it cannot be used very commonly, as well as neither is it biodegradable. So flexible electronics and all, we can go for PLA. Then there is some flexible materials also, like while printing, it will print the same, but it will be flexible afterwards. PETG, like ABS, the full form is written as acrylonitric butadiene styrene, and then polyethylene terephthalate glycol. These are like materials. PLA, most common one. ABS, if you want a perfect like hard type of thing, but that is a bit toxic while printing. And then PETG, that is for flexible ones. So it is somewhat like this one is also a bit biodegradable, but it is mixed with some other materials also. Fine. So in this list, polylactic acid, that is the or PLA, that is the most common one. But you must be aware that there are other things like ABS and PETG that can also be printed, as well as now the people are working towards using metal in 3D print, metal filaments. Though for that, a very high temperature will be needed. So some people are working towards it so that we can print metal objects as well as ceramic, wood, everything is being tried. Okay. Any questions still here?
Not at my end, sir.
Okay. Arvindji, any questions? Okay. So next is in 3D printing, what is the term for digital model that is used to create a physical object? Is it blueprint, prototype, G code, or STL file? A digital model that is used to create a physical object. Yes, any answers on this?
STL files.
STL file, because that is the output of the digital CAD. So that is a model, a digital file that contains the model, how the thing will look like once made, or how the thing will render once done. And that can be used to create a physical file. And G code is the machine code, like from the STL file, when it is cut in pieces, or the proper term is slicing. When it is when this model STL file model is sliced using a slicer, and for every layer a G code is generated, and that is fed into the 3D printers. So still it is like there is now one step, like we generally print in our system, like when we are printing the page, like when we are printing something on a paper, generally we do is that we type in a word and we directly give the command to print it. But here it uses multiple steps, like that has not developed to that level where we directly make a CAD file and directly print it. It is still being done in 2 3 steps. Like first STL is generated, then it is sliced, cut into G code, like converted into G code, and then fed into the 3D printer. Okay. I think I have not put the image of 3D printer. Okay. Uh, Let me show. So when we talk about extruder of 3D printer, what is the purpose of this? Are you aware of what is an extruder of a 3D printer? Yes, anyone?
No, sorry.
No. Okay. Let's go to internet and search one thing. I think yeah. 3D. I think I should have put that. I must. FPPA. Yeah. Let's see. Are you able to see this picture?
Yes.
Yeah. So, okay, I cannot mark in this. Let me open this. Okay, let's copy this. Yeah, Mhm. 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 We are just taking some random 3D printer to understand. Okay. So this part, is this visible? This part where what it is doing is that, uh, let's not see this part. Okay. So are you able to get, like, are you able to hear me?
Yes, sir.
Yes, sir.
Oh, okay. So, like, we saw the filaments, 3D filaments, right? So let's say PLA is kept here. From that filament, one, like, that is having a thread kind of structure, a bit thicker than thread, around 2.75 mm is the diameter of that, or like it. Sometimes it varies. Mostly it is 2.75. Okay, so that is being taken and that is fed into this. Okay, so this is the filament that is going in, and what this does is that it will heat it. This filament will be heated, like, not directly, the whole thing will not be heated, only just like if this is the filament, the last part of it will be heated, and through this nozzle that is known as extruder. And mostly what is done is that the heating part is very close to the extruder. Okay, so it heats, so a melt, and this nozzle will have thicker opening, what smaller opening, not thicker, sorry, smaller opening compared to this 2.75 mm. And from this, the filament will come out, and this whole structure will move, and layer by layer, it will, like, first layer, it will go to those places, and so it will stick. And then at the same time, some fan kind of structure is there that keeps on cooling. Like, heated thing is being put, along with that, it is being cooled. So it solidifies at that instant only, or just in some seconds, 2-3 seconds. And then another layer is put upon it. And since the second layer will be a bit hot, it will it will just melt the upper layer of the previous layer, and it will, like, it will embed, or we can say that it will fuse together. Okay, so this is the extruder. So now let's come to the question: what is the primary purpose of the 3D printer's extruder? Yes.
So I,
Let me just see. Depositing material.
Depositing material,
Yes.
melting and depositing material, right?
Ah,
See, so the purpose is to melt and deposit material. Okay. Okay. Now, this question, I think you might have already got the answer in some way. What is 3D printing also known as? Additive manufacturing, subtractive manufacturing, injecting molds, or CNC machine?
additive
Uh,
manufacturing. Sir. It is additive
add,
manufacturing.
yes, and what? Why this? How this additive manufacturing is
Is it?
different from the common one? Yeah, continue.
We're adding it like layers by layer, multi-layer structure is there. So that's why we are going on adding the different layers
Mhm. And
and
how the?
manufacturing.
What is the common way of manufacturing? If this is additive, is it a
It's a
common way?
molding one.
Molding
Like you just yeah,
and any other
a
molding
screen print. No,
screen,
not a screen.
like manufacturing. When we are talking about manufacturing, that means some solid sub objects we are making.
Hmm, hmm, hmm.
So what generally is done is that we take a block of, say we have to make a gear. What we do is that we take a block of metal, a 3D block of metal, and then it is cut out. it is carved out from that, right? It is cut using CNC machines and further polished, and then it is made. And that is the common one, and that is known as subtractive manufacturing. So we have a object, we remove the things. We remove the things, and the uh, required object is carved out of it, right? Whereas in case of making buildings and all, what we do is that on a empty land, we keep adding things over it. That is additive manufacturing. Fine. Like, to understand the difference, we must understand that when we have something bigger, we remove the things and we get the object. Like some temples also have been made like this, where we have a big rock and we cut out the things. Okay, so that is subtractive manufacturing, and that is the common way manufacturing is done. We take a bigger block, we cut it using CNC machines, we polish it, we do further processing, and then we get the object. Whereas in case of additive manufacturing, we start with plain nothing at all, and then we keep on adding things. So here in 3D printing also, layer by layer, we are adding things. Fine. That is why it is being called as additive manufacturing. And the common manufacturing way is in mechanical, it is subtractive manufacturing. Fine. Any anything you'd like to add or ask?
Sir, what are the two other options? Injection molding. I don't know.
Injection molding is like we have suppose we have a state to make a structure or a statue, you can say some god statue. Okay, and we want to make it of metal. So like you must have seen some thing like where in a sand or not sand molding clay, like you put that object, you press it, and a gap kind of structure for that uh, statue will be formed. And then from making by making a small hole in it, you pour molten metal inside it, or even known as this wax, lost wax.
Yes, sir, I understood.
Got it, right? So that is molding, and CNC machining is somewhat subtractive manufacturing only, if- where we have uh, like computer controlled this cutting, lathe, and this thing. They come under CNC machine. Fine. Any other questions still here?
No, sir.
No. Okay. In PDMS lithography or the soft lithography, what is the primary role of PDMS? To etch patterns on silicon wafer, to serve as photosensitive material, to create microfluidic channel and molds, or to generate electricity.
C, sir.
See, to create microfluidic channel.
Channels and modes.
What role does a curing agent play in the PDMS curing process? Again, the same thing, but in another words. It enhances the UV curing process. It accelerates the polymerization of PDMS. It cools the PDMS to prevent overheating. It softens the PDMS for molding. Yeah. What is the answer?
Sir, B,
B. It
polymerization.
accelerates the polymerization of PDMS. Yes. Any other answers to this? Any other answers?
cell is in D cell.
It's the- It accelerates the polymerization of PDMS, right? Any other role this curing agent plays?
Is it that softening is also possible because of this? It softens the PDMS for molding.
Uh, Curing agent don't have this softening role.
Okay.
Yeah, PDMS itself is soft. Okay, so let's move to the next question. Which of the following is commonly used temperature range for curing PDMS in an oven or incubator? It's 50 to 70 degrees Celsius, 150 to 200, minus 20 to freezing, 500 to 600 degrees Celsius.
So 50 to 70 degrees.
50 to 70. And what if we go to some higher range like 150 to 200 or 500 to 600? What will happen in that case? Like we were discussing earlier also, that PDMS is something that will not be able to resist that much heat. It should ideally be cooled at very low temperatures only. Like higher temperature, it will burn out. Okay, that is why the curing is done at 50 to 70 degrees Celsius. We cannot go beyond this. Beyond this, it will get destroyed. Fine. Which primary factor affects the resolution and layer thickness of a 3D print? So we have now seen how the 3D printer works. So based on this, what are the primary factors that can affect the resolution? That is how thin each layer will be, and layer thickness of it. So these are both same thing only. And sometimes when we are talking about resolution, sometimes the wall thickness also can be considered as resolution. So layer thickness, that is the minimum possible thickness of each layer, as well as if we are making a structure like this, some solid structure like this. So what will be the minimum thickness of this wall kind of structure? How is it determined? What is the primary factor? Is it the color of the filament being used? Size of the build plate, that is what is the maximum size possible for the build to be there, diameter of the nozzle, or the printer's weight? So which is the correct answer? Which of these are the correct answer? Yes, any answers?
The diameter of the nozzle.
Diameter of the nozzle, because as we discussed that it is melting. So whatever was there before this, color certainly color will have no effect on the resolution. Okay, so whatever was the thickness of the filament, that is not relevant now. What is relevant is what how much it is coming out. So uh, when this nozzle like when this filament is being heated and then coming out, so it is the thickness of the nozzle, or the opening, not thickness, I will say opening of the nozzle, that will determine how thick a single strand. Like if you just run one line of it, that is the minimum thing that can be made from it, and that is depending on the diameter of the nozzle. And the printer weight does not play any role. Yes, this can play a role when like one thing that also determines the resolution is that you can have a very thin diameter of the nozzle, but if it is wobbling, like instead of making a straight line, it is making something like this. Are you seeing this line? The mechanical structure is not stable. It is wobbling, like shaking. Okay. So
Okay. Okay.
in this case the resolution will decrease, because instead of making this thin line, it will make a bit thicker because it will have some wobbles. Okay, so this is also a factor, and but that is something like that will depend on the precise like mechanical structure if that is not well made. But generally, it will directly go straight. Okay, so it is the diameter of the nozzle that depends. Bubble formed in a PDMS plus curing agent mix is removed using. I think Arvindji has already given the answer to this, right? So it's incubator, desiccator, or yeah,
That's basically.
it's desiccator. Okay, which is the software used to make designs for 3D printing? It is K-Layout, COMSOL, SolidWorks, MATLAB, Tinkercad, Fusion 360. Yeah, any answers?
SolidWorks is used, sir.
SolidWorks is used, right?
Yeah.
Any other answers?
Tinkercad, sir.
Fusion
Tinkercad,
3.
Fusion 360, yes. Any other? There are a lot more, but like out of this, SolidWorks used, Tinkercad is used, Fusion 360 is used. Even you can use any CAD software like AutoCAD or any CAD software which is used in civil or mechanical engineering, that can be used to make 3D printing designs. But SolidWorks, Fusion 360, Tinkercad, these are dedicated. Like Tinkercad is made used for many other things also, like circuit simulation and object simulation, code coding, and these things also. Fusion 360 is used in replacement of AutoCAD and CATIA Pro E also. So these are all that can be used to make designs for 3D printing. Okay, fine. Till here, any questions? Till here, any questions?
Sir, what is K layout?
K layout,
Here.
I think it is related to this de layout designing software, some layout designing software
VLSI.
for VLSI. Yes, VLSI layout design, LED, K layout, and these things are used in VLSI, I think.
Oh, okay, sir.
Yeah, I'm not sure about K layout. LED, I know. I think it is similar software only. Yeah. Any other questions still here?
No, no, sir.
Okay. Okay. So after this, like Nilmaji said that she wanted a bit revision of CVD and this etching, wet etching, this isotropy and this thing. So isotropy and these things we will cover day after tomorrow. Today we will just cover the CVD thing. Fine. So to understand CVD, we have seen PVD, in which in that case, am I audible? You are able to hear me, both of you?
Yes, sir. Yes.
Yes, sir,
Okay.
it's already.
So PVD we know is that when we have some physical thing already present, like suppose we want to deposit gold, okay, we have a gold target or gold in granular form. We either heat it so much that it evaporates, or we heat it using argon plasma and then it gets sputtered. These are physical vapor deposition, where something is already present, you are just changing the state of it and transferring it on the wafer. Okay. Whereas in case of chemical vapor deposition, some chemical reaction is involved during the deposition. Okay. So there can be two, three different things that are being that are chemically reacting together and forming the product. So if we take a structure like this, Like this is something where uh, mass transport is happening, like gas, some gas and precursor are together flowing, as well as the appropriate heat is being given for the reaction to happen. Generally, reaction happens at higher temperature, like favorable conditions are there at higher temperature. So, in simple words, we can say CVD is a system in which reactant gases are introduced into the chamber. Reaction of gases on the wafer surface results in layer deposition. So we can say uh, generally the reaction is happening in gaseous form. Okay, so along with either the gases itself are the precursors, that means the uh, input reactants, or they might be taking the suppose solid reactant is put here, and there the gas like nitrogen or argon is being flowed, and it is carrying this in gaseous form for the reaction to happen. This tube is generally long. Okay, so what are the steps that happen in CVD? It is simply transport of reactants by forced convection to the deposition region. So we are forcefully putting some gases. So this side actually is closed, as well as this outside will be closed, and then some gas is inserted. Some pressurized gas is being inserted, so there will be a flow. Okay, this is done forcefully. Okay, then is the second one is transportation of the reactants by diffusion from main gas system through the boundary layer of the wafer structure. So if we have a wafer, like here gas diffusion is occurring, yes, yeah, its wafer is not made here, right? So this yellow thing, let's, yeah, this is the wafer here. Okay, so on this wafer, what is happening is that first it is being forced by the airflow to move towards the deposition region where we want the deposition, that is the wafer. Generally it will not be kept flat, it will be vertical or slightly at some angle. So like there is a precursor, say you in a small what I can suppose that in a small structure, uh, we generally call it boat or susceptible. Okay, you have the reactants, and in this reactant it is also getting heated, so certainly it will be able to evaporate, but a forced movement is done using the gas flowing in. So a gas is flowing in, suppose it is getting heated, and a gas stream is coming. So what will happen is that it will take the gaseous molecules with the reactants, it will take with it. So a flow of these reactants are happening, and it is going towards the main stream, like it is going towards the wafer. Like there is a wafer, and that air is flowing, carrying the reactants and coming on the surface, near the surface of the. So wafer is put in the flow of the gas. So gas flow is the wafer is cutting it. Okay, and when this is cutting, so what happens is that these molecules, they will get adsorbed on the wafer surface. Okay, then what happens is that surface processes like chemical decomposition or reaction, that is happening on the wafer. So can I draw on the top, you can see where CVD is written. This part you can see.
Yes.
Okay, so let's say this is the one, we are inserting gas from here, that will result in a flow of gas here, right? Then we have our reactants here. Okay, and this portion is also heated, but at a slightly lower temperature. This is also heated, this is heated, and we are keeping our wafer here. Okay, so what will happen is that this gas comes, and since this is getting heated, it will forcefully take the materials from here and move towards this. And when this wafer is encountered, what happens is that these materials will get on the wafer. These are two different spaces. We want the reaction to happen here. This area, the condition is favorable for the reaction. The temperature is favorable, as well as the surface acts as the platform, surface of our wafer, or on whatever we want to deposit, that acts as the platform on which these reactions will occur. Okay, adsorption, decomposition, surface migration, everything will occur here. So reaction is happening, and then certainly some products will be formed. Let's take one other color. Sorry. Okay, so then some product will be formed here, and along with that, say some gaseous byproducts are being formed. So they will flow from here. So with this flow, they will flow out. So reaction happens, and this whole thing we are studying very slowly, but this is happening very fast. Some reaction is happening, and whatever is the gaseous byproduct, that will flow with the gas. But it is being this flow is being interrupted by the wafer. So, and in this time itself, when it is flowing like this reaction happens, adsorption, desorption, decomposition, everything happens, and it flows out. And this will take out the byproducts from here, outlet. Fine. This is the basic working of a CVD. Okay. And if we see the system, it looks something like this. We have like a very fixed system. This is a very common system, though there are some, this is normal thermal CVD. Okay. So we have control of gases, like different gases. Sometimes we have to put liquid precursor, sometimes like a silane, and these things are put, in which case the gas itself is the reactant. In this case, what I was talking is the reactants are kept here, right, in a susceptible. But in some cases, you can directly give gaseous reactants. If we are not able to like put it, we don't have a solid precursor, then we go for liquid precursor. So one, and there are other gases that will move it forward. These are reactants, then it is going through it, and this whole quartz tube, which can uh, which can withhold a lot like very high temperatures. Okay, and this is actually showing a plasma source, uh, but let's not put that specific one. Okay, in this case, this is a plasma assisted CV, plasma enhanced CVD, but let's remove this for now. So what happens is that we have samples put here. You see in the central part, the samples are put. So the gas is flowing, and suppose here some temperature will be there, followed by some higher temperature, and again lower temperature. Say generally, let's say it's 350 degrees Celsius. This is 850 degrees Celsius, and this is say 400 degrees Celsius. Like generally, heating is mostly done in the central area, but so that there is not much difference of temperature, and cracking of this tube does not happen. So these areas are also heated a bit. Okay. The main reaction will happen in the central area. That is purposefully made like that, that in the central area, these reactions will happen. And then there is an outlet through the pump, it will come out. Fine. And this will actually close. So there are thermocouples above as well as below it. So the heating is being done using circular filaments. Fine. So this is the general way of how CVD works. Is it clear, or am I going very fast?
No, no, yes, sir. It is, and I am getting that your point.
Okay,
You are not fast.
okay. So now, what are the different types of CVD? Generally, we divide CVDs into two parts, like low pressure systems, okay, and high pressure systems, okay. Like they are divided, and there are a lot of types of CVD. The most common ones are like AP CVD, in which the deposition is occurring at atmospheric pressure. No role of pressure is there. Second one is low pressure CVD, in which first, like here you see, vacuum detector was there. The pump to create vacuum is there. So the whole reaction at during the whole reaction, a low pressure is being maintained. Like we are creating vacuum at first, and then whole reaction is happening. Okay, so it will be a bit faster. Then there is plasma enhanced CVD. In that case, we can work at lower temperature itself. Since plasma will increase the energy of the reactants, plasma is being used to increase the energy of the reactants. We can go to a bit lower temperature. Sometimes our substrate are not able to handle higher temperature, so plasma enhanced CVD is used. But as you increase the complexity, the price, as well as the uh, not exactly the price, the cost as well as the complexity of the systems increases. And then high density plasma chemical vapor deposition is there. As well as like there are different MOCVD, and a lot of types of CVD are there, but these are the most common ones like atmospheric, low pressure, plasma enhanced, high density plasma enhanced. Okay. And generally, low pressure techniques are primarily used for silicon dioxide, or polysilicon and silicon nitride films deposition. And high pressure, like normal atmospheric pressure CVD, and these are used for materials like metal oxides like MOS2 and other gallium oxide, copper oxide. This growth can be done in atmospheric pressure CVD also. Fine. So this is a brief about CVD. So did you get what you wanted, or it is still not right?
Uh, no, yes, sir. We got it. I am like little bit confused, like when to go for PVD and CVD, how to like select the right vapor deposition method. So little bit confused in that. I was confused.
Okay.
So now CVD is clear. So I'll just find out further also PVD and
No,
CVD.
it is mostly depending on what different materials are you planning to grow.
Huh. Okay.
It is somewhat like if you make a list of suppose you are going to procure
Huh.
CVD system, then you will make a
Huh.
list of what materials will I generally be growing. So if they are
Okay.
materials that can be simply grown using APCVD, that is the most cost effective one, simpler one.
Hmm.
But yes, it has limitations like it will burn something that is like it will not give that good surface coverage. It will not have
Hmm. Hmm. Hmm.
that good. But it also depends on like if you are able to get the thing that you want, like that will work for fine for you. So why to go for a costlier system, right?
Costlier one. Yes, sir.
Costlier
I
and
got you.
complex. So it is something like we have to think about it, that what are the materials that we are going to grow. Simpler and common materials like MOS2, barium oxide, and these things oxide. Generally, people are working in metal oxides, metal oxide
Okay.
semiconductors, and this for them APCVD is fine, right?
Hmm. Hmm.
But
Okay.
if someone is going for something like depositing silicon or
Hmm.
polysilicon and this thing, so then people go for LPCVD. And when you are going for PECVD, that means it is actually at low pressure as well as plasma is being used. So certainly the complexity is more, as
Hmm.
well as uh, this whole CVD system has one great risk associated with it, is that its byproduct can be toxic.
Yeah. Yeah. Okay.
Okay, toxic byproduct. That is one of very important thing. And if you are going to complex system, the output, like if you are depositing silicon or polysilicon, the silane itself is very poisonous. Okay,
Mm-hmm.
the reactant is poisonous as well as the byproduct is highly toxic. So not just the system, you will have to take care that after the after this the
So,
exit is there.
deposition.
Yeah,
Uh-huh.
after the deposition, the output also has to be treated and properly, like proper treatment of that has to be done. And again, that will involve cost and equipments.
Yes, yes, yes.
So everything has to be taken care of.
Okay. Yes, sir. Thank you, sir.
Yeah. So
So
any
in the
other
next
question?
lecture, you will be covering that how to calculate the each rate in
Yes.
of that process here for isotropic and anisotropic.
Yes, I
Because
will be
I
put.
think in the third or fourth week you have to
Yeah,
explain, but right now I'm not able to get that.
yeah. I will put the like I was about to put that today, but I was not sure like will I
No
be
issues.
able to cover it or not today. That is why I will be
Okay.
covering it in the next class. Anyway, next class
Okay.
is something extra, like whatever
Yeah.
topics you want. Either we can go for revision of that, or
Yeah.
if you
Sir, in the during the exams, subjective questions will also be there.
I
Mm,
think not. But like mostly they will be very similar to the questions that are asked in different assignments.
that's fine.
Yeah,
Okay. Okay.
some calculation part can be there, like isotropy and these things, and I think that is the only
Yeah.
part where calculation is involved.
Yeah, in that is there, and also one more at one more place there was the calculations. I just forgot if I
Mhm.
some related to wavelength and all those things were there.
Mhm. Mhm. That
So
that was resolution of lithography and these things, right?
yes, yes, yes.
Resolution and what is the resolution? That formula is there. Two, three formulas are like numericals. I think they are not much in this course. So they mostly will be theoretical, I think, theoretical with
Okay,
MCQs and these things. But
okay,
for
okay,
that, you will have to check the announcement in the class, like what they are giving, because I am not
okay,
the part of that, questions
okay,
and
okay.
these things. So I'm not sure whether it will be fully multiple choice or it will have combination of this. So you will have to either post or check in the that they will give the description in the course.
Okay, okay, sir.
Yeah.
Okay, sure. I'll just clarify.
Yeah. Yeah. Any
Thank
other
you, sir. Thank
questions?
you.
Yeah. Well. Yeah. So Arvindji, any questions from your side?
No, no, sir.
No. Okay. So thank you all. Uh, See you all in the next.